Welcome back to the deep dive. We're skipping the usual introductory stuff today because the paper we are looking at demands a pretty serious technical breakdown.
It really does.
Yeah, it's DSP. Compiling Declarative Language Model Calls into Self-Improving Pipelines. This is from Omar Khattab and the team at Stanford. And reading it, it feels like a fairly brutal indictment of how we are currently building LLM applications.
Oh, absolutely. It's a paper that basically argues we are stuck in a local maximum. We have these incredibly powerful reasoning engines, but the way we interface with them, manual prompt engineering, is just fundamentally unscalable. It's brittle, it's unscientific, and honestly, for the ML field, it's a bit embarrassing.
That's exactly the feeling I got. We are treating these advanced LLMs like, I don't know, 1950s mainframes.
Yeah.
We're manually punching in string instructions and just sort of crossing our fingers for a deterministic output. And DSPY proposes we just stop writing prompts entirely. We start compiling them. But before we get into the actual compiler internals, I want to push back on the premise a little.
Yeah.
I mean, is prompt engineering actually dead here, or are we just wrapping it in a Python class and calling it programming?
That's the right question to ask. If this were just a fancy wrapper, it wouldn't be worth our time. But the paradigm shift here is moving from manipulating strings to manipulating the optimization process itself.
Okay, unpack that.
So in a traditional pipeline, say your RAG system fails on a complex query. You go into the code, you find the face string that says, you are a helpful assistant who looks at context, and you tweak a few words. You add, think, step by step. In that scenario, you are the optimizer.
You're doing manual gradient descent on natural language.
Exactly. You're the one doing the gradient descent. And DSPY argues that is a massive waste of human capital. It treats the prompt, specifically the instructions and the few shot examples, as the weights of the system.
Right.
We wouldn't manually set the weights of a ResNet layer by layer, so why are we manually cherry-picking few shot examples for an LLM pipeline? We should just define the architecture and let an optimizer find the parameters.
So let's break down that architecture abstraction. The paper introduces these two core concepts, signatures and modules. And looking at the code, a signature looks suspiciously like a Python-type hint.
It essentially is a type declaration, but for a text transformation. A signature just defines the input and output fields. So question, answer, or maybe context, question, search, query.
It's purely declarative.
Yes. You're telling the system what needs to happen, but you are completely abstracting away the how. You don't tell it how to prompt the model.
Which cleanly separates the interface from the implementation. And that implementation is the module, right? This is where the paper's PyTorch analogy feels the strongest.
Precisely. In PyTorch, you have a linear layer or a conv2 layer. In DSPy, you have parameterized modules like dspy.predict or dspy.chainofthought.
But in PyTorch, the parameters are just floating point numbers. If I instantiate a DSPy module, what exactly are the parameters?
The parameters are the specific natural language instructions and, critically, the demonstrations, the few shot examples that get packed into the context window. When you call DSPy chainofthought with your signature, you are creating a layer where the weights are the specific reasoning chains that will guide the model at inference time.
Which is such a massive conceptual shift.
Yeah.
Because we usually think of parameters as the stuff locked inside the model weights, and the prompt is just the user input. But DSPy frames the prompt as part of the model architecture.
It does. And because of that, you get compositionality. Just like you can swap a convolutional layer for a transformer block without rewriting your entire training loop, in DSPy, you can swap DSPy, predict for DSPy, react without changing your application logic. The signature stays identical.
You just change the module instructor. Okay, so we have the architecture, we have the parameters, which are the demos. Now we need the training loop to actually find those parameters.
Yeah.
Which brings us to the teleprompters. I still think the name is a bit goofy, but let's get into what they actually do.
The teleprompter is just their term for the optimizer. It's the compiler backend. The paper focuses a lot on bootstrap few shot. That's the mechanism that actually populates those weights we just talked about.
Walk us through the internals of that, because bootstrapping implies pulling itself up from nothing.
Yeah.
How does it learn the demonstrations if it starts with 0 examples?
It relies on a teacher program. Now, often the teacher is literally just the same model you're trying to optimize the student, but running in a 0-shot setting.
Okay.
So here is the loop. You take your training set, just the inputs. You pass them to the teacher model using a basic 0-shot prompt. The teacher attempts to generate the output. If it's a chain of thought module, it generates the intermediate reasoning steps and then the final answer.
So it's generating an execution trace.
Exactly, a trace. But because LLMs are stochastic and they hallucinate, a lot of those traces are going to be absolute garbage. The logic will be broken, the answer will be wrong, and this is where the metric comes in.
And this is the critical differentiator from standard neural net training, right?
Yeah.
We aren't calculating a gradient here. We're evaluating a discrete output.
Right. DSPY requires a validation metric. For a math dataset like GSM-8K, it's trivial does the final string match the ground truth number. But for a RAG system, it could be a custom Python function checking if the generated answer actually cites the retrieved context.
Right.
The teleprompter evaluates every trace against that metric, and it just brutally filters them. It only keeps the traces where the teacher eventually hit the correct answer.
So it's mining the successful execution paths.
It mines the winning logic, yes. It takes those successful traces, including the weird, idiosyncratic, intermediate reasoning steps the model happened to discover, and compiles them into the few-shot examples for the student module.
So it's effectively doing a search over the space of possible reasoning chains.
It is program synthesis. The program is the set of natural language instructions and examples that makes the pipeline valid. The teleprompter is synthesizing the prompt that satisfies the unit tests, which are your metrics.
It's elegant, but I want to push on the limitations of this teacher assumption. If my student model is a tiny 7 billion parameter model, and my teacher is that same model, what happens if it literally never gets the right answer, zero shot?
Then you hit the cold start failure mode. If your zero-shot performance is exactly 0%, Bootstrap Few-Shot has no successful traces to mine. It yields an empty set.
The gradient is flat, metaphorically speaking.
Metaphorically, completely flat. In that scenario, you have two options. One, you manually craft a tiny handful of seed examples to jumpstart the search. So yes, a tiny bit of manual prompt engineering. Or two, you use a stronger teacher. You use GPT-4 to generate the traces, and then you compile those traces into the prompt for a local Llama 2 model.
Which seems like the absolute killer feature here. It's distillation via compilation.
It is. You're distilling the reasoning capabilities of a frontier model directly into the context window of an edge model. And the empirical results in the paper really back this up.
Let's actually talk about those results. They benchmarked on GSM-8K for math and Hotpot QA for multi-hop retrieval. And looking at the tables, the numbers that jumped out at me weren't the GPT-4 numbers. It was the T5 results.
The T5 results are arguably the most profound part of the entire paper. They took T5 large, which is a 770 million parameter model. Tiny. It's a toy model by modern standards. They compiled a DSPY pipeline for Hotpot QA on it. And the result was that it was competitive with GPT 3.5 prompting.
A sub 1 billion parameter model competing with a model that is presumably, 100 or 200 times its size.
And we have to be clear about why. It's not because T5 has some magical latent capability.
Yeah.
It's because the complexity of the multi-hop task was offloaded from the model's internal weights of the pipeline's architecture.
Right.
The compiler found the exact sequence of demonstrations that taught T5 how to decompose a query, retrieve a document, read it, and answer.
Which really challenges the whole scaling laws narrative we constantly hear. Or at least it suggests that for specific domains, just throwing parameter count at a problem is basically a crutch for bad pipeline programming.
That is the deeper theoretical implication here. We often conflate intelligence with a model's robustness to vague instructions. GPT-4 feels smart because it can figure out what you want, even if your prompt is terrible.
Exactly.
But if you can compile a perfectly precise set of instructions and examples, a so-called dumb model like T5 becomes highly capable in that narrow vertical.
Let's dig back into that optimization loop, because the paper also mentions Bootstrap Few-Shot with random search and MIPRO, which is the multi-prompt instruction proposal optimizer. These are doing a lot more than just filtering traces, right?
Right, because basic Bootstrap Few-Shot is just a greedy approach. It grabs the first K examples that pass the metric and stops. Random search, or the Bayesian approaches like Optuna that they mention in the appendix, treat the selection of those demonstrations as a literal hyperparameter search space.
Okay, so how does that work in practice?
The search space is the set of all subsets of your Bootstrap data. The optimizer grabs a combination of, say, 5 examples, runs the dev set, checks the metric, then it throws those out, tries a different combination of 5, and evaluates again.
Which is incredibly computationally expensive. You're running inference over the validation set over and over.
It is expensive, but think about the alternative. The alternative is you, the researcher, tweaking a prompt, running the dev set, getting a coffee, coming back, tweaking it again. You are just moving the computational cost from expensive human time to relatively cheap GPU time.
That's fair. But there's our constraint here we haven't touched on, which is the context window.
Yeah.
You can't just shove 100 successful traces into the prompt.
Right. It's a constrained optimization problem. You have a token budget. The optimizer has to find the most informative subset of examples that fits in the window and maximizes the metric. But this is exactly why Bootstrap fine-tune becomes relevant.
Ah, right. The paper mentions that DSPY basically unifies prompting and fine-tuning.
This is where the framework really shines. If your optimized prompt gets too long, or you just want faster inference, you can take all those Bootstrap traces, which, remember, are high-quality gold data created by your own pipeline, and use them to update the model weights directly.
Without changing the DSPY script.
Exactly.
Yeah.
The program code is identical. You just switch the compilation target from prompt to weights.
Which completely solves the data scarcity problem for fine-tuning. Usually, getting high-quality chain-of-thought data for a weird, specific domain is incredibly expensive.
Yeah.
Here, DSPY is just generating it synthetically using that teacher-student loop.
Yes, it's dynamic synthetic data generation tailored exactly to the pipeline logic you defined.
I want to pivot a bit to the comparison with existing tools in this space. The authors take some pretty direct shots at libraries like LangChain and Llama Index. They call their approaches brittle. Is that just academic shade? Or is there real technical validity to that critique?
There is real technical validity. If you look at the source code of those libraries, at least at the time this paper was published, they are just riddled with hard-coded prompt templates. Massive strings like "you are an AI assistant" buried deep in the Python source.
Right.
And that is hidden technical debt. If you import a standard LangChain summarization chain, you are inheriting a prompt that was likely hyper-optimized for Text DaVinci 003 or maybe GPT 3.5 Turbo.
Yeah.
If you try to run that exact chain on Llama 3 or Mistral, it's going to be suboptimal because those models have entirely different token distributions and preference manifolds.
And DSPY doesn't have any strings.
The DSPY library itself contains basically 0 handwritten prompts. It generates them dynamically based on the signature and the specific model you pass it. It's agnostic, which makes your pipeline truly portable. You swap models, run dspy.compile, and it adapts the prompts to the new model's specific quirks.
Okay, let me play devil's advocate for a second. There is a massive complexity cost here. Writing a string is easy. Anyone can do it. Defining signatures, building parameterized modules, writing custom metrics, and orchestrating a compilation loop that is hard. It feels like we are trading prompt engineering for pipeline engineering.
We absolutely are. But that's the trade-off of any compiler abstraction. Writing assembly by hand is easier than setting up a C++ build chain if all you want to do is print "Hello World." But if you are building an operating system, you need the compiler. DSPY is total overkill for a weekend chatbot project, but for a complex, multi-hop reasoning system with retrieval, self-reflection, and logic, that complexity is necessary.
Let's talk about the metric dependency, because that feels like the real bottleneck. The paper relies so heavily on the existence of a good metric. But in a lot of generative tasks, creative writing, open-ended summarization metrics are notoriously unreliable. Auger and VLU scores are totally useless for semantic meaning.
This is undoubtedly the Achilles heel of the entire paradigm. DSPY is strictly bound by the quality of your metric. If your metric is exact match on a math dataset, it works beautifully. If your metric is fuzzy or proxy-based, the optimizer will just exploit the fuzziness. It will find a prompt that hacks the metric without actually improving the output.
Goodhart's law in action.
Exactly. Now, the authors do argue that we can use LLMs as judges. You can write a DSPY metric that literally asks GPT-4, is this summary accurate and concise?
But then you're just optimizing against the latent preferences of GPT-4.
You are. It becomes a distillation of GPT-4's preference model. But notice how this differs from something like RLHF. In RLHF, we train a reward model on human data and use PPO to update model weights. Here, we are defining the reward function programmatically, maybe using an LLM, and we are optimizing the input context, the prompts, rather than the weights.
Though, as we said, we can update the weights too. It really feels like this framework sits somewhere between AutoML and program synthesis.
I would argue it's actually closest to neural architecture search, or NAS. In traditional NAS, we are searching for the best graph of convolutional or attention layers. In DSPY, we are searching for the best graph of text interactions.
Right, the program is the text transformation graph.
And the parameters are the natural language instructions. What's mathematically fascinating here is that the search space is discrete and totally non-differentiable, and yet these relatively simple heuristics like Bootstrap Few-Shot work surprisingly well.
Why do they work so well? Does it imply the optimization landscape for prompts is just smoother than we thought?
That is a huge open research question right now. The success of this implies that there are many, many good enough prompts in the token space. We don't actually need to find the global maximum. We just need to find one of the many functioning prompts in a dense cluster of valid solutions. Humans are just terrible at finding them because we can't intuit high-dimensional token spaces.
Let's look at a concrete example of that from the paper, the thought reflection pipeline. I thought this was fascinating because it wasn't just a straight A to B chain.
Right. It beautifully demonstrated compositionality. They built a pipeline where one module generates a thought, a second module explicitly critiques that thought, and a third module resolves the conflict to produce the final answer.
In a string-based approach, managing the context window and the handoffs between those three personas is a nightmare.
It's spaghetti code. But in DSPY, it's literally just prediction generator X, critique critic X position, final resolver X prediction critique, and then you compile the whole stack together end to end.
And the optimizer figures out how they need to interact.
Exactly. The optimizer might discover that the critic module needs to be prompted to be highly aggressive in order to actually help the resolver module get the right answer.
It discovers the necessary behavior of the submodules to maximize the final output. That is wild. It's basically backpropagation of intent, but without gradients.
Backpropagation of intent without gradients? That's a perfect way to summarize it. It creates a coherent system where the components organically align rather than a Frankenstein monster of random prompts pasted together.
Okay, so where does this break down? If I am an ML researcher listening to this right now, what are the open problems I should be looking at?
The biggest one is the credit assignment problem.
Okay.
In a very long pipeline, say you have a 50-step agent, if the final result is wrong, which step actually failed? Bootstrap Few-Shot essentially assumes that if the final answer is right, all the intermediate steps were right. And that is a massively strong assumption.
Because the model could hallucinate step 3, but just happen to luck into the correct final answer at step 50, and now we are treating that bad trace as gold training data.
Exactly. You get spurious correlations baked into your prompts. We desperately need better ways to validate and assign credit to intermediate reasoning steps without requiring human labels for every step.
What about generalization?
That's the second major open problem. Does a prompt optimized on GSM-8K generalize to other math domains? Or did the optimizer just overfit to the specific phrasing of the training set? The paper suggests the compiled prompts generalize fairly well to similar distributions, but we really don't know the mathematical limits of that yet.
And I assume the cost is still a factor. Running these compile loops, especially with GPT-4 as a teacher, is not free.
It's definitely an upfront compile time cost, but the engineering argument is that you amortize that cost over the lifetime of the application. You spend $50 compiling once, and then you deploy a highly efficient local model forever.
I want to wrap up by zooming out to the big picture implication here. We touched on T5, competing with GPT 3.5 earlier. If the DSPY paradigm truly succeeds and scales, does it change the trajectory of frontier model development?
I strongly believe it shifts the core value proposition. Right now, the entire industry race is about building the smartest, most massive general-purpose model. But DSPY points to a future where the smartest model is essentially just used as a compiler.
Right.
We won't use GPT-5 or Gemini Ultra to serve end-user queries. We will use them in the back end to write the programs and optimize the prompts for 1 billion or 7 billion parameter models that actually run the inference on the edge.
It's compiled specific intelligence.
Exactly. We stop trying to serve everything from a monolithic God mode AI. We use the God mode AI to synthesize millions of tiny, hyper-optimized experts. And DSPY is providing the initial syntax for how we actually structure that compilation.
It literally turns the LLM from a conversational chatbot into a piece of a broader software stack.
It turns NLP into a proper engineering discipline. We are moving from alchemy, stirring the string pot and hoping we get gold, to chemistry, where we actually understand the structural bonds and the reactions.
And I suppose for anyone currently managing a team of prompt engineers, that might be a terrifying or liberating thought, depending entirely on how you look at it.
If you're a prompt engineer right now, my advice is to stop writing strings and start writing evaluation metrics. That is where the field is going.
That is extremely sound advice. The paper is DSPY. Compiling Declarative Language Model calls into self-improving pipelines. It is dense, it is highly technical, and if you're building with LLMs, it is absolutely worth your time to read. Thanks for listening to this deep dive. I'll leave you with this to mull over. If frontier models just become compilers for edge models, what does that mean for the economics of inference APIs in 2 years? Something to think about.
See you next time.